Alright, in this video I'm going to go through a couple more U-substitution practice problems, starting with the integral of sine of 3x dx. Again, I'm looking for the composition of functions here to figure out what u should be. I don't know what to do with sine of 3x, but if I can make that look like sine of u, I would know how to integrate that. So I'm going to let u be equal to 3x. I'm going to differentiate both sides to get du equals the derivative of 3x to the first, just becomes 3. I'm going to move the dx over, and I need to ask myself, what do I still need to replace here? I replace the 3x, but the term that still has an x is that dx there. So my goal is to make this side of the equal sign just look like dx, so I have something to substitute in there. So I'm going to divide out the 3 to get 1/3 du is equal to dx, and I'm going to make that substitution into my integral. So I'm going to write the integral of sine of u, and instead of dx, another expression that represents dx is 1/3 du. Now you'll never see me write it like this because constants, I can multiply them in any order, right? So I'm just going to write that constant on the outside of the integral. That's one of my properties of integration. So the integral of sine of u is just negative cosine of u. And again, you could check yourself by differentiation. And I'm going to substitute that value for u back in to leave it in terms of x. So my final answer here is negative 1/3 cosine of 3x plus c. And again, you could always check yourself by differentiating this to show that you get back to sine of 3x. For number 2, it looks like 4 plus x squared is a good candidate for who u is. Because if I take the derivative of that, I think I'm going to get that 2x anyway. So let's just see what happens. If I let u be equal to 4 plus x squared, take the derivative, du equals, remember the derivative of a constant is 0, so that's just going to go away. For x squared, I could bring down the exponent and subtract 1 from it. And I'm going to bring the dx over. And notice what you have to replace is just 2x times dx. Because right now what we have in our integral is the integral of u to the 10th times 2x times dx. Remember, it doesn't matter what order I multiply these terms in, so I could just move the 2x next to the dx to make it more obvious that that expression is the same thing as du. So I'm going to replace 2x dx with just du. And remember that du in the integral sign is just telling me to take the antiderivative of whatever's in between there. So the integral of u to the 10th du is just u to the 11th over 11 plus c. And I'm going to substitute back in for u, right? U was just 4 plus x squared to the 11th over 11 plus c. And again, you can apply a chain rule just to make sure you get back to that integral there. For number 3, a little bit more going on here, right? But cosine of radical x looks like it's going to be a little ugly. If I could just make that look like cosine of u, I might be able to work with that a little bit better. So I'm going to let u be equal to radical x. Now notice that's not the same thing as the radical x in the denominator, because that's really more like an x to the negative 1/2 because it's in the denominator. So it's not like I'm replacing u in two different spots here. Now to make it easier to differentiate, I'm going to change that radical to an exponent of 1/2. So u is really equal to x to the 1/2. And if I take the derivative of that, I could multiply by 1/2 and subtract 1 from the exponent. 1/2 minus 1 is just negative 1/2. Now again, that should be du, right, because I took the derivative. This is still kind of hard to look at, and I generally don't like leaving negative exponents. So I'm going to rewrite that as du equals, I'm going to bring that x to the negative 1/2 down to the denominator, just so I can make it a positive exponent. And remember that x to the 1/2 is the same thing as radical x. There's a reason why I'm leaving it like that. So what I see here is that I currently have cosine of u. And if I rewrite it, I'm just going to separate this to see what I still have here. I still have a 2 times radical x in the denominator, and I still need to get rid of that dx, which should be pretty satisfying because that's precisely what du equals. Right, so the fact that I had 2 radical x in the denominator really doesn't complicate things because I could just replace all that with du. So again, this integral is a lot easier to look at than what I started with. The integral of cosine of u is just sine of u plus c. And again, I'm going to make the substitution back in for my final answer of sine of radical x plus c. So the hard part here is figuring out what u is, and then actually taking the derivative and writing it in a form that looks like something that appears in my original integral. For number 4, I have the integral of e to the x over e to the x plus 1 times dx. Now, it might not be obvious what to make u here, but you have 2 options, right? U is either going to be the numerator, or it's going to be the denominator. Now, what I'm thinking in my head is if I let u be the denominator, if I take the derivative of this, the derivative of e to the x plus 1, e to the x just turns into e to the x, and the 1 just goes away because it's a constant. So if I take the derivative of what I have in the denominator there, I'm actually left with exactly what I want to still replace there. So this is more of a trial and error one. You could make u the numerator, see what happens, and you'll get stuck when you get to this step. But if you make u the denominator, again, if I separate it, it might make it more obvious what happens here. I'm left exactly with what I still need to replace in terms of x, an e to the x and a dx. So I'm going to rewrite this as the integral of 1 over u times du. Remember, 1 over u is one of those special integrals. The antiderivative of that is just the ln of the absolute value of u plus c. I'm going to make the substitution back in to say that this is the same thing as ln of the absolute value of e to the x plus 1 plus c. For number 5, again, it looks like u should be ln of x because that's my composition of functions. If I could just make that u squared in the numerator, I know how to take the antiderivative of that. So I'm going to let u be equal to ln of x. Again, the derivative of ln of x is just 1 over x. And here's what I have right now. I've got u squared over x dx. So I need to get rid of an x in the denominator and a dx. We actually already have something that represents that. If you're having trouble seeing that, try separating them. I've got a u squared in the numerator times a 1 over x, right? Because if I were to simplify that, I'd get back to what I started with there, times dx. And this whole expression right there is the same thing as du. That's what this equation says right here. That should happen every time when we do U-substitution. Either I get exactly what I need to replace, or it differs by a constant that I need to divide out. So the integral I'm trying to take here is just u squared times, instead of 1 over x dx, I'm going to replace that with du. And that lets me take the integral with respect to u now. So remember the reverse power rule. I'm going to add 1 to the exponent and divide by it, plus some constant that I don't know. And I'm just going to replace what u is, right? U is ln of x. So I'm left with ln of x cubed plus c is my final answer there. For the last example, number 6, it looks like if I make u that exponent there, I would know how to work with e to the u. So I'm going to let u be equal to x squared. I'm going to take the derivative on both sides. The derivative of x squared is just 2x. I'm going to move dx over again. And look at what we have here. We've got the integral of, we've got an e to the u, we've got an x, and we've got a dx. Now, I only need to get rid of x dx, and my current expression for du says 2 times x dx. So to fix this, I'm just going to divide out the 2 to find that 1/2 du is equal to x times dx. So I'm going to take this expression right here, the 1/2 du, and just substitute that in for x dx. So my integral in terms of u is just the integral of e to the u times 1/2 du. But again, it would make more sense to write that constant on the outside because it doesn't change how I think about integration if I'm just multiplying by a constant. Right, so the antiderivative of e to the u is asking you, who is this the derivative of? And remember that e to the u doesn't change, so that's just e to the u plus c. And again, if I make my final substitution back in for u, I get e to the x squared plus c.